Good morning everyone. I hope you all in good health and high spirit. Welcome to today's lecture on the fundamentals of electroencephalography, explaining the basic principles of EEG. Now let us discuss how electrodes placed on the scalp detect and record electrical signals generated by the neurons. If we talk of the basic principle of the EEG, it operates on the fundamental principle that the brain activities generate electrical signals due to the communication between neurons. These electrical signals, often referred to as brain waves, are crucial indicator of brain function, cognitive states and neurological disorder. The EEG detects and recording process including the following steps. The first one is electrode placement. EEG begins with the placement of the electrode on the scalp. These electrodes are typically positioned in specific patterns and configurations to capture the electrical activities from different regions of the brain. The second one is electrical potential. Neurons communicate by sending electrical signals in the form of action potentials. When millions of neurons work together, they combine electrical activity generated measurable potential difference on the scalp. The third one is extracellular current flow. When the neuron fibers ion movement creates brief changes in electrical potentials in the extracellular space, this extracellular current flows leads to voltage fluctuations on the scalp, which can be detected by the electrode. The next step is amplification and recording. The voltage fluctuations are extremely small and required amplifications to be detectable. EEG equipment amplifies this signal to make them suitable for recording. The amplified signals are then recorded as a time series of the voltage change over specific interval. The fifth step is signal processing. The recorded EEG signal is often subjected to various signal processing techniques. Filtering is commonly used to remove unwanted noise and focus on a specific frequency band of interest. Additionally, data can be segmented to analyze a specific event or brain status. Finally, the interpretation step. The resulted EEG waveform is presented graphically as a series of wave pattern with different frequencies. Each frequency band is associated with different cognitive and physiological state. Now, the challenges and the considerations we are facing while recording EEGs are scalp conductivity. The conductivity of the scalp, skull or brain tissues influence the propagation of the electrical signal. The skull acts as a barrier, distortion and attenuating the signal. Different tissues having different resistance affecting the recorded signal quality. Volume conduction. Electrical signals generated by the neurons spread across the brain and the volume conduct through the surrounding tissues. As a result, the signal recorded at specific scalp electrode represent the summation of the activities of various brain regions. Reference electrode. EEG signals are relative, meaning they are measured with respect to a reference electrode. The choice of the reference electrode can impact the interpretation of the recorded data. The next factor is artifact removal. EEG recording can be affected by various artifacts such as muscles activity, eye movement and electrical interferences. These artifacts need to be identified and removed to extract the true brain activity. In summary, EEG is based on the principle of detecting and recording the electrical signals generated by neurons during their communication. Through the strategic placements of electrode on the scalp and amplification of the signal, EEG provides valuable insights into the brain function, cognitive process and neurological disorder. Through careful concentrations of challenges, and accurate interpretation is crucial for meaningful analysis. The different brain wave pattern alpha, beta, theta and gamma and their associated status. Certainly, the brain patterns are distinct electrical oscillations that can be observed in electroencephalography recording. Each brain pattern is associated with specific mental status, cognitive process and physiological conditions. Here is an overview of the different wave patterns and their associated status. Alpha waves, its frequency ranges from 8 to 13 cycles per second. Alpha waves are typically observed when a person is awake, but in relaxed status with closed eyes. They are often associated with calm and peaceful mental status. Alpha waves are commonly present during state of meditations, deep relaxations and daydreaming. The second wave is the beta wave. It ranges from 14 to 30 hertz. Beta waves are sent when a person is awake, alert and actively engaged in mental activities. They are linked to focus attention, problem solving and cognitive process. Beta waves are prominent during tasks that required concentration, logical thinking and active decision making. Theta waves, its range from 4 to 7 hertz. Theta waves are often associated during light sleep, daydreaming and creative thinking. They are associated with dreamy and imaginative mental status. Theta waves can occur during the early stage of sleep, during the state between wakefulness and sleep and in states of deep relaxations. The next wave is the delta wave. Its frequency ranges from 0.5 to 4 hertz. Delta waves are primarily seen during deep sleep stage, include slow wave sleep. They reflect a state of unconsciousness and restorative rest. Delta waves are most prominent during sleep when the body and mind undergo essential repair and relaxation process. The next wave is the gamma wave. It ranges from 30 to 100 hertz and even higher frequencies. Gamma waves are linked to heightened cognitive processing, attention and complex problem solving. They are thought to reflect synchronous neural activity across the multiple brain region. Gamma waves are associated with the tasks that demand integration of sensory informations and coordination of various brain areas such as precision learning and consciousness awareness. It is important to note that the association between brain wave patterns and specific mental state is not always straightforward. Brain activity is complex and influenced by a various of factors, including the individual variation context, external stimulus. Additionally, brain wave patterns can overlap and change rapidly depend on the ongoing mental process. While the relationship between the brain patterns and mental status is still being explored, under this pattern provides valuable insight into the brain dynamics nature and its response to different cognitive and physiological conditions. The role of the frequency and amplitude in interpreting the ECG data is very important. The frequency and amplitude are the fundamental components of EEG data. They plays a crucial role in interpreting the electrical activities of the brain. They provide the valuable insights into the brain function. Different brain wave patterns are categorized based on their frequency ranges. Each brain wave pattern correspond to specific mental states and cognitive process. As we have already seen, the alpha, beta, theta, delta and gamma waves. Abnormal frequency patterns can indicate neurological disorder. Amplitude is also playing an important role in diagnosing. Amplitude reflects the magnitude of the neural synchronization or desynchronization. Larger amplitude includes more synchronized firing of neurons, while smaller amplitude signifies more desynchronized activities. Higher amplitude in certain frequency band can signify distinct cognitive processes. For instance, during focus attention, beta waves amplitude tend to be higher. Now, let us discuss the various applications of the EEG. Certainly, the EEG has a wide range of applications in biomedical field. Here are some of the key applications. in clinical diagnostics, aiding in determination of EEG is primary tool for diagnosing and monitoring the epilepsies. EEG is an essential for diagnosing various sleep disorders. It tracks sleep stages, breathing patterns and disruption in sleep cycle. EEG is used to monitor the brain functions in patients with traumatic brain injury. EEG is widely employed in cognitive research to study brain responses to various stimulus, tasks and cognitive processes. It provides insight into how brain process information, attention, memory, decision making and emotional reactions. EEG based brain computer interfaces allows individual with severe motor disabilities to communicate and control external devices using their brain signal. This technology translates EEG patterns into commands for computer applications, robotic device and assistive technology. So, these are the various aspects of EEG. With this, we come to an end of today's session. Thank you everyone for being such a wonderful and engaged audience throughout this session on electroencephalography. Your participation and attention has truly made this class a rewarding experience. It is fascinating to see your curiosity and enthusiasm for delving into the world of EEG. As we come to an end of today's lecture, I want to take a moment to express my heartfelt appreciations to each and every one of you. Before we conclude, I want to appreciate your decisions to learn and your enthusiasm for today's topic. Your engagement has made my role as an educator incredibly fulfilling. Remember that learning is a continuous journey. I encourage you to explore EEG further and discover the countless opportunities it holds. With that, I do like to thank you once again for joining me today. Your presence and participation has made this lecture a meaningful experience for all of us. I wish you all the best in your academics pursuit and beyond. Thank you and have a fantastic day.